Yep.
Good morning, everyone. Welcome back to the latest seminar in our seminar series for the Australian Geometric PDE seminar series. This morning, it's my pleasure to introduce to you Jack Thompson. Jack is currently at the university, a PhD student at the University of Western Australia, and he's going to talk to us about overdetermined problems involving the fractional Laplacian. Thanks very much, Jack.
Okay, thanks, Tim, and thanks to the organizers for running this seminar series. So today I'm going to be talking about an overdetermined problem involving the fractional Laplacian. So throughout this talk, I want to start at the very beginning. So we've got So I want to begin at the very start with what I mean by overdetermined problems, and slowly build up to discussing the actual problem we're interested in. So if anyone has any questions at any point, please feel free to stop me and ask, and I'll hopefully answer the question right there and then. Okay, so first of all, what do I mean by an overdetermined problem? So an overdetermined problem is a problem in PDEs where we have a well-defined PDE, and then we want to impose an extra condition on the solution of the PDE. Okay, and this leads to the problem being overdetermined. So not every single region will satisfy this extra condition. So how you want to think about it is you've got a physical situation which is modeled by a PDE. And then as an engineer, say, or a physicist, you might want to look at a specific situation where you have where your solution has beneficial properties, and then you want to classify which in which situations your solutions have these nice properties. So it has a very strong connection with domain optimization. So the actual classical example, which I'm going to go through in a moment, arises in fluid dynamics, but these kinds of problems have applications in beam mechanics, in optimal heating, and in population dynamics, just to name a few. So so the goal when we look at these overdetermined problems is to classify the regions which admit solutions to the PDE and the overdetermined problem. So the emphasis is no longer really on the solution, but on the region that the solution is defined in. Okay, so I'm going to go through the classical example of an overdetermined problem, which is called Serrin's problem. And the motivation is in fluid dynamics. So we imagine that we have a straight pipe, okay, and it has a constant cross section, which we're going to denote omega. And just for simplicity, omega is in R2 because the pipe is in 3 dimensions. And then we suppose that we have a viscous incompressible fluid that's flowing through the pipe. And we also assume that its streamlines stay parallel, so there's no turbulence. So we're in a really nice situation. Now, if you go through the physics, you can define what's called the streamline function. And you can check that the streamline function satisfies that the minus Laplacian of the streamline function u is, well, so it's constant in omega. So if I select units that make all the constants go to 1, then it has minus Laplacian u equal to 1 in omega. And then we also have this Dirichlet boundary condition that u is 0 on the boundary, and this is a common condition in fluid dynamics. Now, we also impose this overdetermined condition that the Neumann derivative of u is constant on the boundary. And what this says is that the tangential stress exerted on the pipe is constant. So this is beneficial from an engineering standpoint, because as soon as you have differences in stress on the object, this leads to fatigue quicker. So if it's constant, then you would hope that the pipe doesn't break for longer. Now, Serrin, James Serrin proves in 1971 that in this situation, you have to have that omega is a disk. So there's no other shape that satisfies, that admits a solution to this equation, like with all these three properties. So this is the idea, right? So we're given a solution to a PDE. We impose an extra condition called the overdetermined condition, and then we want to classify the regions that admit a solution. Okay. So actually, Serrin proved a much more general result. He actually proved the following theorem. So first of all, there was nothing special about R2. So we take omega to be in Rn, and it's a bounded domain with C2 boundary, and F is locally Lipschitz. And then if we have a positive solution, U, which satisfies this semi-linear equation, as well as it has constant Neumann derivative on the boundary, then omega is a ball. Okay, so some important things to mention. I do have to impose that the solution is positive. And this is due to the method of proof, which is the method of moving planes, which I'm going to discuss in more detail later in the presentation. So actually, as soon as we drop this positivity assumption, all bets are out of the window. In fact, without this positivity assumption, this kind of problem is still open in general.
So Jack, you're saying no counterexamples or anything, just nothing's known in that situation?
Well, I'm not certain about counterexamples. Certainly, even in the simplest case, so if you take F to be, say, a constant times by U, so you've got an eigenvalue, Dirichlet eigenvalue. This is open, and there are no counterexamples in that situation. I'm not sure.
That's really concerning if even in the linear case you can't say anything.
Yeah, and so I'll discuss later why this is really an issue, but it is to do with the method of proof, which is this method of moving planes, and the method of moving planes strongly relies on maximum principles, which will require that U is non-negative. So yeah. Now this method of moving planes is actually an incredibly powerful and versatile technique for not just overdetermined problems, but other symmetry problems. So for example, a very famous application of the technique was by Gidas, Nie, and Nuremberg, who used it to prove symmetry of solutions to semi-linear problems in a ball. Okay. So there's been many generalizations actually of Serrin's problem. And the problem I'm looking at today is a generalization of Serrin's problem. So first of all, it's been generalized to nonlinear equations. So things like the P Laplacian, and then viscosity solutions of fully nonlinear equations. Another direction it's been generalized is onto manifolds. So for example, a similar result to the theorem I just gave on space forms is true. So another thing we can do is we can change up the overdetermined conditions. So the overdetermined condition before was the constant Neumann derivative. So we could change this and see how that affects the problem. And actually, this is one of the ways that we change Serrin's problem. Now, another way, another generalization is to maybe not impose the overdetermined condition on all of the boundary, for example, but only on a portion. And in this situation, maybe we can't expect omega to be a ball because we've only imposed this condition on part of the boundary, but we could still say things about maybe the shape of omega. We can say things about the regularity of the boundary where we've imposed this overdetermined condition. So this is actually very closely related to free boundary problems, which are a form of overdetermined problems, but with much more relaxed over conditions. Like in a free boundary problem, we're not imposing the overdetermined condition on all of the boundary, but just on a small part or a small on a curve in the domain. And the other way we can generalize it is to alternate operators. So this is what we do as well in our project, where we generalize it to the fractional Laplacian, which I'll also discuss later.
Hey, Jack, in all of these examples, are we mostly interested in elliptic sort of steady state type problems, or is there much parabolic theory in here as well?
I'm not so familiar with the parabolic theory. It's often stated with elliptic PD, but yeah, I'm not too familiar with the parabolic theory, unfortunately. But
yeah, no worries. Thanks.
Yeah, thank you. So, what is the generalization that we consider? So we call it the parallel surface problem. So this is the setup. We have G, which is a bounded domain, and we take omega to be G plus BR, so the Minkowski sum of G and a ball of radius R. And the Minkowski sum of two sets is defined in this way. And so what this looks like is that we have this set G, and omega is a bigger set, and the boundary of omega is parallel to the boundary of G, and it's a distance R from G. Now, in the local case, the parallel surface problem is this. So this was proved by Chirallo, Magnanini, and Sakaguchi in 2015. So we have the same setup as I just mentioned. G has a C1 boundary, and it satisfies, this should say, the uniform interior ball condition. So at every point in the boundary of G, there's a ball that's a subset of G that touches the point, the point on the boundary. And we suppose that there exists a positive function, U, and it satisfies this semi-linear problem. So we have, it satisfies, minus Laplacian u is f of u in omega. It has Dirichlet boundary conditions, but this time we impose that u is constant on the boundary of G. Okay, so just to go back to the diagram, so in omega, we satisfy our semi-linear PDE. On the boundary of omega, u is 0, but on this curve here, which is the boundary of G, we impose that u is a constant. So this can be seen as a discrete version of Serrin's overdetermined problem. So if we imagine we had an infinite family of these parallel curves getting closer and closer to the boundary of omega, then this is going to give us the original Serrin's problem. An infinite family of curves getting close to the boundary of omega that u is constant on. Then this implies the original Serrin's problem. So the fact that we're only imposing it on one parallel curve makes it a kind of discrete Serrin's problem. So the theorem states that in this situation, omega has to be a ball, and hence G is also a ball because the boundary of G is parallel to the boundary of omega. So now I want to just change pace a little bit and discuss the fractional Laplacian. So the fractional Laplacian is a non-local or an integro-differential operator that's given by the following singular integral. So here S is in the interval 0, 1. CNS is just a normalization constant. And by PV here, I mean the Cauchy principal value. So it's not exactly clear from this definition, but the fractional Laplacian is actually a generalization of the usual Laplacian, right? So the reason why we call it the fractional Laplacian is because it satisfies the following properties. So first of all, if we take one fractional Laplacian and then we apply another fractional Laplacian, well, this is the same as applying the fractional Laplacian of you sum the two orders. And also, when we take the limit of S back up to 1 of the fractional Laplacian, we recover the original minus Laplacian. So in this sense, it's a fractional analog of the Laplacian.
Hey, Jack.
Yep.
I wondered if you could just make a couple of comments about why you need to take the principal value there. You know, what goes wrong with this integral. People might be interested in that who aren't familiar with these things, perhaps.
Yes. So certain functions. So for example, if you take linear functions, you can have issues with this kernel if you don't include the principal value. So the principal value allows you to define the fractional Laplacian for certain functions that if you didn't include this, it wouldn't necessarily exist. So actually there is a definition of the fractional Laplacian that doesn't use this principal value. But in order to move to this definition, this form of the definition, you need to introduce the principal value. Otherwise, things that are well defined for that definition become undefined in this definition.
Yeah, I suppose the issue is just that, like, the power of n plus 2s, like that's just too big. So since you're insisting on s being between 0 or 1, I guess that's just too big to make this thing actually integrable. So you need to workarounds to actually get this thing defined, right?
Yeah, so in order to make this well defined, you really need two ingredients. First of all, you need some sort of integrability condition, which makes it defined because we're integrating over Rn. But actually, it's not altogether clear at the start, but you actually need some differentiability of u close to the point you're evaluating at to make this u of x minus u of I overcome the singularity in the x minus y on the bottom. So, for example, if u is C2 about the point x, that's enough to make this well defined without the principal value if it's C2.
Am I right in thinking that C alpha is enough, like Holder continuity is enough as well, or am I way off there?
Well, you can, so if you have C2s plus epsilon about the point, plus some integrability condition, then you're all good. But C2s isn't enough.
Yep, cool.
Yep.
Thank you.
Yep, that's all right. So the fractional Laplacian actually satisfies some maximum principles and the Harnack inequality, for example, but they have to be adjusted to this non-local setting. So for example, with the Harnack inequality, for the local equations, you need to impose that u is non-negative in just the domain, where for the non-local Harnack inequality, u has to be non-negative in all of Rn. So that's why we call it non-local, because suddenly you have to impose these conditions on all of Rn as opposed to just the region your equation is in. Okay, so what is the problem that we actually considered? So so suppose that G is a bounded set. So this is the same setup as before. We take omega to be the Minkowski sum of G and a ball, and F is locally Lipschitz. So I prove with Serrin, Dipierro, Giorgio Poggesi, and Enrico Valdinoci that if we have a non-negative solution that's Holder continuous up to the boundary, that is not identically zero and satisfies the fractional semilinear problem with Dirichlet boundary conditions. So something to note here is that the Dirichlet boundary conditions are now in all of is in Rn minus omega. So this is a consequence of the non-locality of the fractional Laplacian. And we also impose u is constant on the boundary of G. Well, this implies that u is radially symmetric, that u is positive in omega, and that omega and G are a ball. So I should mention that this problem was considered for the particular case that f equals 1 by Ciraulo, Dipierro, Poggesi, Pilastro, and Valdinoci in 2021. So they looked at this problem and also the stability of this problem, which we'll discuss later as well. So what is the strategy of the proof? So the proof uses this method of moving planes. So there's a bit of notation with the method of moving planes, but the idea is very simple. So we have our domain omega, and we pick some direction. So in this case, I've just set the direction to be the E1 direction, so 1, 0, 0, 0, with n minus 1 zeros. And we define a plane which we're going to slide from right to left across our domain omega. And when we slide this plane, we're going to take the part of omega that's on the right of the plane and reflect it across the plane. So the notation we have here is h lambda is the half space on the right of the plane, and then sigma of lambda is the part of omega that's on the right of the plane. And then I just put a little dash to denote the corresponding region that's been reflected to the left-hand side of the plane. And then the idea is we introduce a new function, which is the anti-symmetric part of u across this plane. So it's the odd part with respect to reflections across the plane. And what we want to show is that as we move this plane left, we keep moving it until it can't go any further, until this reflected part wants to jump out of omega. And then at this point, we want to show that v is equal to 0, because what that would mean is that v is actually an even function with respect to reflections across the plane. And then if we can do this for every single direction, it means E is an even function in every single direction with respect to some plane. And this means that U has to be radially symmetric. Okay, so when we do this, depending on the shape of omega, there are two possibilities that can occur. Like geometrically, there are two things that can happen. So first of all, the reflected part of omega becomes internally tangent to the boundary of omega at some point that's not in the plane. And the second thing that can happen is that the plane reaches a position where it's orthogonal to the boundary of omega at some point. So to illustrate these two cases, I have a bit of an animation. Okay. So this is just in Desmos Online. So a shape like this is in case 1. So I have my moving plane here, which I slide from right to left. And at some point, it intersects omega. And then I reflect the right-hand side of omega across the plane. And I get this green shape. And as I keep going, eventually, the reflected part intersects the boundary of omega internally. So it becomes internally tangent at this point. And if I keep sliding t, it comes out of omega. So this is case 1. Case 2 is something like this egg shape. So as I slide my plane, it reflects, but it doesn't become internally tangent. The issue is that at this point here, my plane is orthogonal. Sorry, the normal of my boundary is included in my plane. So actually, as I keep pushing, my reflected region sort of pushes outwards. Okay, and so when we go through the method of moving planes, you need to consider these two cases separately. So remember, we've defined v lambda to be this reflection, the odd part of u across this plane with respect to reflections across the plane. Now, you can show that v lambda satisfies a linear PDE with a 0th order term. And this 0th order term is given by this. Now you can see v lambda is non-negative in the left-hand half plane minus the left-hand part of the reflected part of omega. And this is where the maximum principle is going to come in. So if we don't assume that u is non-negative, we no longer have this condition. And so then we don't have the maximum principle anymore. And basically our goals are, we have two goals. First of all, that when lambda is greater than the critical time, so when I say the critical time, this is the value of lambda where one of either case 1 or case 2 occurs. So we first want to show that when lambda is greater than the critical time, that v lambda is non-negative in Rn. And then we also want to show that when lambda is equal to the critical time, v lambda is equivalent to 0. So this means that u is an even function with respect to reflections across the critical plane, the plane at the critical time. Okay, so the idea for when to prove that when lambda is greater than the critical time, v lambda is non-negative, is so we first let m be the value of lambda where our plane first intersects omega, or the closure of omega. And so when lambda is very close to m, but less than m, the volume, so by the vertical lines I mean the volume of the left-hand part of the left part of omega, the reflected part of omega, is very small, is very close to 0. So this means the first Dirichlet eigenvalue with respect to the fractional Laplacian is very large. And actually, in this situation, we can apply the maximum principle, even though we don't have a sign on the 0th order term. So normally you need a sign on the 0th order term to be able to apply the maximum principle. But if the first eigenvalue is very large, you can still apply the maximum principle. And this allows us to conclude that v lambda is non-negative, at least for lambda in this case. And in fact, you can use the strong maximum principle to show that in this situation, we actually have v lambda is strictly bigger than 0 in the left-hand part of omega. And then what we do is we define m tilde to be the smallest value of lambda for which this holds. And then we just argue by contradiction that m tilde actually has to be the critical time. So we get that v lambda is positive for all lambda bigger than the critical time. And this implies this statement up here. So something to note is this doesn't actually use the overdetermined condition at this point. This just uses properties of the PDE. Now, where we need to use the overdetermined condition is at this point here. So when lambda is equal to the critical time, we want to show that it's equivalent to 0. And we prove this by contradiction. So we know that from the strong maximum principle, v lambda is either equivalent to 0 or it's strictly positive in sigma prime lambda. And then we consider our two cases that I talked about before. So in case 1, when we become internally tangent, so we become internally tangent at this point, because G is parallel, the boundary of G is parallel to the boundary of omega, the boundary of G, the reflected part of the boundary of G becomes internally tangent to the boundary at G at this point. But then since U is constant on the boundary of G, this means that V has to be 0 at this point. But we assume that V lambda, sorry, this should be V lambda here at the critical time. But we assumed by contradiction that V lambda was strictly positive. So the fact that V of P is 0 contradicts that assumption. Now, in the second case, we can argue that the x1 derivative. So first of all, we have this Q, which is this point here, where E1 is tangent to the boundary of G. And so we get this by, again, using the boundary of G is parallel to the boundary of omega. And at this point, we can show that the derivative in the x1 direction is 0. Now, this isn't a contradiction at this point, so we need to obtain some kind of contradiction. And the contradiction comes from the following lemma, which was proved with Dipierro, Poggesi, and Valdinoci. So we proved that if we have a super solution of this 0th order equation, where C is bounded, and that U is antisymmetric across the x1 equals 0 plane, and we also have that U is non-negative in Rn plus, so that's the right-hand side of the plane, and U is strictly positive in the in B1 plus, which is the part of B1 where x1 is positive, then actually at 0, we have to have this strict inequality. So this is a Hopf type lemma. Now, something to note is that if you're familiar with the boundary regularity of the fractional Laplacian, you might actually expect you only expect U to be Holder continuous up to the boundary. So it's in some sense surprising that we get a derivative here and not some kind of S derivative. And this actually really comes from the fact that U is antisymmetric. So because of this antisymmetric assumption, this lemma is essentially an interior estimate, which you can think about by reflecting B1 plus across the x1 equals 0 plane. And then the strategy of the proof is identical to the proof of the original Hopf lemma. So you construct a barrier from below, which gives you this strict inequality. But actually, the construction of this barrier is very different to the original Hopf lemma. So in the original Hopf lemma, you use exponential functions, which don't necessarily work so well with the fractional Laplacian because it's this singular integral. But instead, you can take advantage of the non-local properties of the fractional Laplacian to come up with this barrier. And from here, this this result here, this the fact that the derivative in the x1 direction at q equals 0 contradicts the previous Hopf lemma. So this proves the result. Now, in the final 5-10 minutes or so, I want to just quickly discuss some further problems that are being looked at. So an interesting problem is actually to do with the stability of these overdetermined problems. So the idea is, instead of saying, suppose we have a PDE plus an overdetermined condition, instead we say that, okay, we have a solution to the PDE, but we almost have this overdetermined condition. So we're very close to the overdetermined condition. Does this mean that the region omega is almost a ball? So it's a stability, it's a stability problem, because we're really saying if the overdetermined condition is slightly perturbed, is omega still close to a ball? So the answer in general depends on what we mean by almost, which is probably not surprising. So in certain situations, the answer is yes. In certain situations, the answer is no, depending on what we mean by almost. So something that can go wrong, for example, is you can have kind of bubbling phenomena. So if you imagine taking two balls, disjoint balls, but they just touch. So you have a kind of dumbbell shape with a very thin neck. Then this can almost satisfy the overdetermined condition in some sense of almost. But this is not almost a ball, right? It's almost two balls. So for this particular problem, how we define almost, so how we define u being close to a constant on the boundary of G is through this Lipschitz semi-norm on the boundary of G. And how we measure omega being close to being a ball is through this rho of omega, which is if we take the largest possible ball on the inside and then the largest possible ball on the outside where both balls are at the same point, and then we consider the difference in their radii, then that's what this rho of omega denotes. Now, this is a theorem in an upcoming work, again with Serrin, Dipierro, Giorgio Poggesi, and Enrico Valdinoci. And basically, it says that under certain assumptions, this is the inequality we get. So we can control rho of omega using this Lipschitz quantity. And this is when this Lipschitz semi-norm of u is sufficiently small. So here, some things to note is that I have this weird S Neumann derivative, and this is because, as I mentioned before, solutions to fractional problems are only in general Holder continuous up to the boundary. So it no longer makes sense to define the Neumann derivative on the boundary. So instead, we have to consider this S Neumann derivative at the boundary. So there has been work on this problem in the past. So in the case S equals 1, this was actually proved by Ciraulo, Magnini, and Sakaguchi in 2016. And for the fractional Laplacian, this was looked at by Ciraulo, Dipierro, Poggesi, Pilastro, and Valdinoci in 2021. And they considered the case that f is equal to 1. So this is the torsion problem. And they did get a stability result, but they got this power of 1 on s plus 1 on the Lipschitz quantity of u. So this is suboptimal, because when we take s back up to 1, we don't actually recover the linear bound that was proved by Ciraulo, Magnini, and Sakaguchi. So we get, when s goes back up to 1, we get a power of a half, which is suboptimal. Okay, and so the idea of the proof with these stability type of problems is to repeat the method of moving planes as we did before, but every time we make some kind of qualitative estimate. So for example, we apply the strong maximum principle. We want to replace this by a quantitative estimate. So for example, we replace the strong maximum principle by the Harnack inequality, because the Harnack inequality quantitatively measures how far away u is from being equivalently 0 if it has a point that's close to being 0. So an important step towards doing this in the non-local case is the following theorem. So in the local case, you can just take the usual Harnack inequality and bring it straight over and just apply it as is. But you can't actually do this in the non-local case. And the reason is because for the non-local Harnack inequality, you actually need to impose that U is non-negative in all of Rn. But also in the non-local case, but for the method of moving planes, we want to consider functions that are anti-symmetric with respect to reflections across a plane. Now, the only functions that are non-negative in all of Rn and anti-symmetric across a plane is the zero function. So the usual non-local Harnack inequality isn't applicable to the method of moving planes. So instead, you need to prove a Harnack inequality for anti-symmetric functions. And that's what this result is. So this is an anti-symmetric Harnack inequality. Now, once this result has been established, then you can work through the process as in the local case. So first of all, you show that your Vm, which is your anti-symmetric part of U at the critical time m, can be controlled by the Lipschitz semi-norm of U in the reflected part of Gm. From there, you need to use boundary estimates to prove this following technical result. But once you have this inequality, you can combine them to prove that the distance of x to the boundary of G can be controlled by the Lipschitz semi-norm of U. And this is on the boundary of, so we've got the reflected part of G, we've got the part of G on the right-hand side of the plane, and then we take the closure of that, and then we take the boundary of that. So this is basically saying that when this Lipschitz quantity is small, the boundary of the reflected part of G is very close to being the boundary of G. And once this inequality has been established, you get the stability estimate. And this proves the theorem. So that's all I had to say. Thank you, everyone, for listening.
Thanks very much for your time, Jack.
Were there any questions?
I have a quick question. Yeah, so you introduced the Serrin problem at the start.
Yes.
And then this sort of generalization of that involving the parallel surface.
Mm-hmm.
Can you make sense of a Serrin problem in the non-local setting, or could you put a condition on the Serrin derivative? I mean,
and I should have mentioned that actually. I forgot. This was looked at by Jarisch and Four. So they considered the Serrin problem where you've got your fractional semi-linear problem, Dirichlet boundary conditions, and instead of constant Neumann derivative, you have constant S Neumann derivative, and they prove exactly this result. Yeah. Okay, nice. Is there what about the stability result? Is there? I don't even know if that's true for the classical Serrin problem, but does that work in that sort of limit case in your setting? For the classical Serrin problem, the stability has been analyzed. The difficulty actually comes in with the classical Serrin problem because you have estimates up to the boundary. At the moment, they still haven't got what they believe to be the optimal estimate. So they get this log term appearing, and this is because you need to make estimates up to the boundary because you've got the overdetermined condition is imposed on the boundary. For the classical version of the discrete Serrin problem, so the parallel surface problem, I mentioned that's been solved, and it's actually easier because you're on a parallel surface, everything's interior. So in that situation, it's much easier to analyze. For the non-local case, I actually don't know of any stability results for the non-local Serrin's problem.
Yeah. So you couldn't deduce something somehow as a, I mean, so, okay, another question is, can you reasonably interpret that non-local Serrin problem as somehow a limit of these problems that you consider? And could you get estimates on the limiting result as a limit of your estimates in any sense?
So you're saying that given the non-local
yeah, I mean, something you want to interpret that you'd like to relate that. Yeah, you'd want to relate it to something where the separation goes to zero.
Yeah. So
right.
As long as I actually believe that this result I mentioned at the end, that you can recover the local case. What you just have to make sure that you've done is the constants you get stay uniform as s goes to 1, and I don't think there would be any issue in that situation. Yeah, I don't think that would
thanks.
cause any problems.
Nice.
Yeah.
Are there any further questions for Jack regarding his talk? All right, then let's thank Jack again for a nice talk.
Thanks. Yeah, nice talk.
Thank you.
I'll stop recording now. Thanks, everyone.